Child pulls a wagon by the handle along a flat sidewalk. So the force applied is directed at 30 degrees above the horizontal. All right. Remember that if she's not able to lift it up, she's not doing any vertical work on this. And under quick inspection, I guess we're not given any details about the mass of the wagon, but I'm sure it's heavy enough that it doesn't float off into the sky. So this is 80 newtons projected at an angle of 30 degrees from the horizontal. So work is equal to force times distance times the cosine of theta. 80 newtons times the distance of 12 meters times cosine of 30 degrees. (831 joules of work). All right. The force of friction. So the work due to friction is equal to force of friction times distance, times cosine of theta if you want to include that in. So 34 newtons times 12 meters times the cosine of 180 degrees. It's just another way of injecting that minus sign in there. All right, so 34 times 12 gives you 408 joules negative. As for the total work that's accomplished in this, that's the work due to the child plus the work attributed due to friction, which performs negative work. So 831 joules plus negative 408 joules will give you the answer of 423 joules of total work. You can also think of this as net work if you want to, but we never call it that. We just call it total work. Number 2. A tow truck pulls a car from rest on a level road. A tow truck exerts a horizontal force of 150 newtons and the frictional force, or 1500 newtons, and the frictional force on the car is 810 newtons. Calculate the work done by each of the following forces on the car as the car moves 12 meters. The force of the tow truck on the car. So calculate the work, right? Yeah, the work is equal to the force of the truck times the distance. So 1500 newtons times the distance of 12 meters. (18 kilojoules of work). How about the force of friction? Again, friction is in the opposite direction of travel, as you can see over here. So negative 810 newtons times your 12 meters. Negative 9720 joules. And if the friction was greater than your forward work, no, it's not going to start accelerating backwards. That's impossible. You got to keep in mind that friction, it's a value that's a maximum. In other words, it will perform up to this value. It shouldn't be any greater. Otherwise, then friction can just move things. All right, and that can't be the case. All right. I think the last thing, the normal force. Well, the normal force in this case over here is, well, we don't know the mass, but we know it doesn't move upwards. All right. So work due to the normal force is equal to the normal force times distance. And even though we don't know the mass of the car, because it doesn't move in the y dimension, the normal force, or the work due to the normal force, is equal to 0 joules. Same as with regards to the work due to gravity. As it's not sinking into the ground, it works up to 0 joules as well. As for number 3, calculate the displacement of the bucket. I think that's just from kinematics. So VI is equal to 0 meters from rest. VF is equal to A is equal to 2.2 meters per second squared, and delta T is equal to 3.0 seconds. and we're trying to look for our delta D. Delta D is equal to VI delta T plus 1/2 A delta T squared. VI goes to 0, so it's a lot cleaner to solve. 1/2 of 2.2 meters per second squared times 3.0 seconds squared. So 1.1 times 9 would be 9.19, isn't it? Why am I using a calculator? 9.9. 9.9 meters. Calculate the work done by each force acting on the bucket. So, as for the rope itself, that's equal to the force applied vertically acting on it. Wait. F is equal to mass times acceleration times delta D. We have those values. So a mass of 2.0 kilograms accelerated at 2.2 meters per second squared by a distance of 9.9 meters will give us 39.6. .9. Whoopsie daisy. There you go. 43.56 joules. As for part B, we got to start off with a free body diagram. All right, so tension is equal to, nope, MA, we assume upwards is positive, is equal to tension minus mg. So tension is equal to MA plus mg, or MA plus g. So the mass of 2.0 kilograms multiplied by an acceleration of 2.2 meters per second squared against the force of gravity will give us a tension of 24.02 newtons. So the work due to the tension is equal to force of the tension times the distance that's moved vertically. So 24.02 newtons times the vertical ascension of 9.9 meters gives us 237.8 joules. What about the work due to friction? Or not friction, work due to gravity. Well, that's just mg delta h, but because gravity is going in the opposite direction, it will be a negative value. All right, because you're trying to lift it upwards, but gravity is pointing in the opposite direction. So negative 2.0 kilograms times 9.81 newtons per kilogram times the height that's moving at, which is 9.9 meters. If you feel more comfortable doing cosine of theta for the minus sign, by all means, by the way. All right, so 9.81 times 2 times 9.9 gives you 194.2 joules. If we need to find out the total work, that's equal to the work of the tension plus the work due to gravity. So the positive work due to tension plus negative 194.2 joules is equal to 43.6 joules. calculate the net force acting on the bucket and the work done acting on the net force. Well, we know that the net force is equal to T minus mg. We solve for T. (24.02 newtons). Subtract 2.0 kilograms times 9.81 newtons per kilogram. So 24.02 minus 19.62 will give you 4.4 newtons. That's your F net. And if you do the work of your net, interestingly, you'll see that it works out the same answer as your total work. So 4.4 newtons times a distance of 9.9 meters will give you the same answer as before. So that's what I meant by before, that your total work is effectively your net work, not that you ever call it net work. How much work is done by an Olympic triathlete who accelerates herself on her bicycle from 5 meters per second to 10 meters per second? Once again, guys, do not subtract 10 from 5 and expect it to work out. You have to sit down and calculate it out in its entire. So, start off with your givens. VI of 5.0 meters per second, VF of 10.0 meters per second, and we know that our work is equal to delta EK, which is equal to 1/2 mvf squared minus 1/2 mvi squared. And if the mass remains the same, then why not just factor it out? That will make your life a lot easier. So it's 52.5 times 100 subtract 25, which is 75. Why am I doing that? I don't know. 52.5 times 75 will give you 3938 joules. 2 sig fig, I would write this down as 3.9 kilojoules. It takes 185 kilojoules of work to accelerate a car from VI of 23 meters per second to VF of 28.0 meters per second. Solve for mass. Well, I'm just going to be lazy and I'm going to use this formula here for the next one. So when I isolate for m is equal to 2w divided by VF squared minus VI squared. So it's about deriving out the equation and isolating for m. So 2 times 185,000 joules over 28.0 meters per second squared minus 23.0 meters per second squared. Just remember in your calculator to put in brackets where necessary. So 2 times 185,000 divided by, and you'll want to open bracket for your denominator, because you're doing 28 squared minus 23 squared, close bracket. And then that'll tell you the curb weights. Awesome. Number 6, a fighter jet is launched from an aircraft carrier with an aid of its own engines. And what do we have? We have the force of the thrusters, which is 2.3 times 10 to the 5 newtons. And the distance it travels is 87 meters, and the EKF is 4.5 times 10 to the 7 joules at liftoff, assuming that EKI is equal to 0. All right, well, with the free body diagram, we have the fighter jet, and we have two forces acting on it, aside from the normal force and the force of gravity. And I think we're pretending that the force of friction doesn't matter. So you have the force of the thrusters and you have the force of the catapult, both pulling it in the same direction. And we're trying to figure out how much the catapult helps speed it off. Because with most fighter carriers, there's my tower right over here, there's my takeoff thing. Unfortunately, the length of this is just way too short for a plane to reasonably take off. Look at that, all right? Most athletes can run 87 meters, so it's not that much distance for a plane to try to take off. All right. Yeah, most athletes can run that in 10 seconds or so. So the only other way to make it speed up quickly enough is by including a little slingshot hidden underneath the carrier's landing on their platform. All right, just quickly whips it off. So let's figure that out. What do we know so far? We know work is equal to force times distance, and we know that work is also equal to the change in kinetic energy. So EKF, oh, there's another work as well. So the work in total is equal to the work of the catapult plus the work due to the thrusters. So 1/2, EKF minus EKI is equal to WC plus WT. Again, we said that EKI is equal to 0, so we have our EKF. We just need to solve for the work due to the catapult plus force of the thrusters times distance. So the work of the catapult is equal to EKF minus FT times delta D. So 4.5 times 10 to the 7 joules, subtract 2.3 times 10 to the 5 meters, multiplied by 87 meters. Three, 6, 7. 2.5 times 10 to the 7 joules.